Morning, AP Chem. So we are continuing with Unit 3. In our last video, we looked at the intermolecular forces themselves. Now what we are trying to do is look at the solids and the states of matter. All right, so just as a reminder, when we think about the state of matter, our solid, they're really close together. The liquid, they can move past each other. The gas, they're very far apart. All right, but what keeps the solids together, and why do the gases not stay near each other? All right, so let's just think about room temperature. So approximately 25 degrees Celsius, 298 K. I know typically when we do STP, we use 0 Celsius, 273 K, but I just want to think about room temperature. Our solids, they have high melting points, all right, which means they have not melted yet. And they have those because they have really strong attractions. The solids have strong attractions, so they stay together. Now, our gases, anytime we have a gas at room temperature, that means it has a really low boiling point, which means it has already boiled and now it's in that gas phase. And our gases at room temperature, they have really weak attractions. All right, now the liquid is kind of the in between where we have a lot of play. The liquid, we can go back and forth. But when we're thinking about a liquid, a lot of liquids that we see typically have boiling points before 100 degrees Celsius. So they will easily boil with a little bit of heat, but maybe not at room temperature. So just going through the notes from the College Board, all right, now our intermolecular forces, they can explain the physical properties of a material. This is an important feature of the intermolecular forces, and this is an important feature of Unit 3 in the curriculum. All right, so many properties of liquids and solids are determined by the strengths and types of intermolecular forces present. All right, so that's why we need to know the different types of forces, all right, because intermolecular forces are broken when a substance vaporizes. So here in this picture, we're looking at a molecular view of water, all right? And we know that from the surface of a liquid, a molecule might have enough kinetic energy and it might break away. It's breaking its own intermolecular forces and leaving the liquid phase to go into the gas phase. So those intermolecular forces are keeping it in the liquid phase, all right? And that's what's gonna get broken when we talk about a substance vaporizing, all right? So the vapor pressure and boiling points are directly related to the strength of those interactions. Different molecules will have different types of intermolecular forces, and based on how strong or weak those are, that's how we'll come up with their vapor pressure and their boiling points. All right. Now, the melting points also tend to correlate with interactions, but because the interactions are only rearranged in melting, the relations can be more subtle. All right. What that's saying is when a substance melts, all right, they're still in close contact from the solid to the liquid. They're still in close contact, so there still are intermolecular forces. There are still those attractions happening, but it's been rearranged. It's typically more organized in the solid and it's a little looser in the liquid phase, whereas to go from liquid to gas, it has to be broken. All right, so now particulate level representations showing multiple interactions are going to be useful. This is a really big feature. What I want to point out in this image of our solid water, all right, is solid lines will be used for chemical bonds, all right, covalent bonds, solid lines. The dashed lines will represent the attractions. And these are the types of diagrams that the College Board, they're going to generate on the test. They're going to put together some kind of image that you couldn't have found in a Google image search or something, and they're going to ask you to analyze it, all right? That's a very common theme in the free response questions. So we really want to be in tune with this idea that the dashed lines represent the attractions. Solid lines are always going to represent covalent bonds. All right, now we're going to think about the different types of solids. So our first one is the ionic solid, right? Our lattice, all right? Positive, negative, positive, negative, positive, negative, positive, negative. All right, now our lattices, they have low vapor pressures, all right? They have such strong attractions that we don't get any sublimation happening. We don't get the substances leaving the solid phase, or if it was in the liquid phase and becoming a gas. So low vapor pressures, right? Because there's really strong attractions in that ion-ion attraction. All right, high melting points. It's going to take a lot of energy to get the solid to deform. All right, and even when it's in the liquid phase, they'll still be near each other, but they'll be free. But it's going to take a lot of energy because of, again, that ion-ion attraction is just so strong. All right, high boiling points as well. Now, we will see with the melting points that if we're looking at the same cation, it'll actually decrease as we get bigger elements. All right, now that's a little counterintuitive at first because typically we've seen in previous things that the intermolecular forces get bigger as the atoms get bigger. But in the ion-ion attraction, it comes down to Coulomb's law, and it's due to the distance. So a sodium ion, it can actually have a stronger attraction to fluorine because it can get closer to fluorine than it can to chlorine or bromine or iodine. All right, the other thing to keep in mind too is the charge. The sodium is +1, all of the anions are -1. If we change the charge, obviously that changes. We think about that when we do like the lattice energy. But just something to keep in mind with ionic solids, we want to know how close they can get to each other. All right, so again, we see the melting points. Lithium and fluorine, those are both in period 2, so they can get really close to each other. Sodium and chlorine, all right, now these are bigger atoms, so they're a little further apart. Their melting point decreases. Potassium bromide, even smaller. The rubidium iodide, right, really big atoms, a lower melting point, all +1 and -1 in this example. All right, now they tend to be brittle. So if we stress them, if we can get the lattice to shift just 1 unit over, all of the positives will line up and they'll actually repel each other, and all the negatives will line up and repel each other. So that's why they're brittle, but they can conduct electricity only when dissolved in a liquid, which we've seen plenty of times, or if they are molten. All right, when we melt an ion, or an ionic compound, I should say, the ions are free in that molten liquid phase. All right, think about anytime we've represented a liquid, they can slide past each other. So we have the positive and negative ions able to slide past each other. They still retain their ions, right? So it's still positive and negative, but now they can move around. All right, now a covalent network. All right, a covalent network, the classic example is diamond and graphite, 2 different versions of a covalent network of carbon. All right, they are covalently bonded together. So when we look at the diamond diagram, all right, we see all solid lines. I want you to ask yourself, do you see any dashed lines in the diamond network? And the answer is no. So we're not thinking about intermolecular forces happening here. These are all covalent bonds, all right? Carbon bonded to other carbons. And a covalent bond is really strong, all right, relative to just an intermolecular attraction. Now the graphite, it is in layers, right? These 2D layers, and those are covalent bonds, so we see them as solid lines. In between the layers, right, vertically, we see the dashed lines. Those are the attractions. All right, now diamond is incredibly strong, graphite not as strong. All right, so now these are only formed from non-metals, right? So when we think about a covalent network, it's got to be non-metals. It can be an element, right, like carbon, or it can be a binary compound. It'll only be a binary compound, though. You will not see larger molecules. So right here we have silicon dioxide, we have silicon carbide. All right, now due to the strong covalent interactions, covalent solids will have high melting points. All right, so when we're adding that energy to try to melt a covalent solid, it has to break those covalent bonds. All right, and that is going to require a lot more energy than breaking apart an intermolecular attraction. Right, it's breaking an actual covalent bond, not an intermolecular attraction. All right, and something really important about the 3-dimensional network, all right, they are rigid and they are hard because the covalent bonds, their angles are fixed. So if we look at the SiO2 in glass, or in quartz, I should say, the covalent bonds are fixed. All right, when we think about that diamond structure, all of those covalent bonds, those bond angles, they are fixed, and that gives it that really rigid, strong structure. And that rigid, strong structure explains why it has the high melting points, things like this. All right, now something like graphite is soft because it has adjacent layers that can slide past each other. All right, so the more three-dimensional the network is, the much stronger it's going to be. Think about the diamond. Now, for some of these structures, they're only in 2 dimensions. So we have layers of them. They're not quite as strong. All right. Now, this is a picture of a carbon nanotubule. So it kind of is like the graphite, but it's actually wrapped around and it makes these tubes. And it's actually something that comes up a lot in science fiction, but it is actually a real thing. These carbon nanotubules are incredibly strong. So if we could make materials out of it, these could be really strong materials for like soldiers, things like that. All right, but it's this covalent network. And if they could make several thousands of these tubes again and again and again, weaving them, each tube is going to be really strong, all right, because it's all covalent bonds. And this is a carbon nanotubule. All right, now, after the covalent network, we're talking now about molecular solids. All right, now molecular solids, they're composed of distinct individual units of covalently bonded molecules. This is really important. They are distinct. They are individual units. So individual H2 diatomic molecules, individual O2 diatomic molecules, individual P4 diatomic molecules, individual S8 molecules, not diatomic, excuse me, individual CO2s, individual waters, individual glucose. But each molecule, it's distinct and it's individual. Now, they're going to be attracted to each other through relatively weak intermolecular forces. All right, now, the molecular solids generally have a low melting point because of the relatively weak forces present between them. So here we have the water molecule. All right, this is solid water. So each water, each H2O, it's its own distinct thing, but there are attractions between them. Now, water is one of the stronger molecular solids because it tends to form a crystalline shape. Most of them are amorphous, right? So these attractions actually kind of get organized, whereas that's not often the case. All right, so here it's carbon dioxide that you can kind of just move about, and we're using those dashed lines to show the attractions. All right, solid carbon dioxide we know as dry ice, and if you have that at room temperature, it is subliming. It is not even spending time in the liquid phase. It's going right from solid to gas. All right, so fairly weak attractive forces in our molecular solids. All right, they do not conduct electricity. Their valence electrons are held really tightly. All right, and they can be composed of very large molecules or polymers. All right, all of our organic compounds, all right, if they are at the solid, they are molecular solids. All right, so we're thinking about our sugars. We're thinking about solid organic acids, right? Like benzoic acid, right? We've used that in lab. So so we can get molecular solids with these much larger molecules, the polymers, all right? So just something we've seen before. So now our metallic solids, right? Metallic bonding, all right? Metallic solids, good conductors of heat and electricity. A metallic solid, we could just think of something as like a sheet of copper, right? All of those copper atoms are next to each other, and what they have free valence electrons. All right, so what ends up happening, we call this the sea of electron model. All right, so the atoms are kind of all in place, but the valence electrons are able to move about. All right, so our group 1 metals, they have these valence electrons moving about. Our group 1 metals, something like pure sodium metal, it is super soft. All right, it is very easy. You can cut it with a butter knife because you are able to move, like those electrons, they're free, they could move about. All right, and it doesn't matter, you know, if it's a group 2 metal. So think about like our magnesium ribbon, we've used that in lab. We could bend it back and forth with our fingers and break it, right? All of those magnesium atoms, they have that +2 charge, and then the electrons are about it. Now, none of the metals on their own are electrically charged because they do have the electrons balancing out the positive charges of the the nuclei, all right, but they can conduct electricity really easily, right, because of those electrons being free. Now, they tend to be malleable and ductile, right? So malleable, if you hit a solid, a metallic solid with a hammer, right, you may move some of those atoms, but that sea of electron, it'll adjust, it'll kind of move with them. So you can deform a metal, but it won't necessarily break, it won't shear, it won't rip apart like a brittle ionic solid. All right. And then ductile, that is stretching it into wire. So in wire, if we were to think of that, I don't have an image of it, but all of the nuclei would kind of be lined up in a row. That would be it stretched out. But the electrons are free. They could still move about it. All right. Now, alloys. Two types of alloys are substitutional alloy. We're substituting one metal for another. All right. So a common example of that is brass, where you have copper and zinc substituted. But copper and zinc, they're both metals. They contribute. They both contribute valence electrons, and they're roughly the same size. Right. So you're just kind of mixing them up. But it's the interstitial alloys. All right. Interstitial alloys, they have small atoms in between the atoms of the metal, all right? And they tend to make the lattice much more rigid. Now that decreases its malleability, that decreases its ductility, but it does make them very strong. So our classic interstitial alloy is steel. All right, steel, it is several iron atoms, but we have these tiny carbons that go in between them, and they hold those iron atoms kind of in place. They make it a little more rigid. They make it so that they're not able to slide past each other. So no longer ductile, no longer malleable, a little more brittle now, all right, but really strong. They're not going to have those repulsions like the ionic solids will, all right. And again, that's the sea of electron molecule. Now the last thing, the College Board keeps liking to throw out these large biomolecules or polymers. We don't spend a lot of time with them. All right, we're not going to do something like looking at protein folding, anything like that. Right, that's more of like an AP bio topic. But just something to remember: the functionality of a biomolecule and its properties have to do with its shape, and its shape is going to be based in part on intermolecular forces throughout the molecule. Right, so the shape of some of these molecules, whenever they fold over, it's one section of the molecule being attracted to another. All right, so there are a lot of important non-covalent interactions happening in these large biomolecules or these polymers. All right, something that if you go on in chemistry, you will certainly see more of in like an organic chemistry class or a biochemistry class, but not something that you should really worry about too much, but they might use it as a prompt. All right, that's an important thing. All of these different topics, all of these different solids, they are often prompts in the free response. They'll show you pictures, so you just have to be able to analyze them. All right, so that is the solids and the liquids. All right, excuse me, that is the solids. Gases, you know, we're going to look at the ideal gas law for that. The liquids, will look at things dissolving in solution, but for the most part, we know solids and liquids, because the molecules are close to each other, that's why they have the definite volumes. Our gases, the molecules are not close to each other. They can spread out indefinite volumes. All right, solids, we know they have the definite shape because of how close they are, and they're not able to really move apart, whereas liquids have that indefinite shape because they can slide past each other. One last thing I didn't mention, amorphous solids. Those are solids that don't have a defined shape. Most of what we looked at in this slide was crystalline. Ionic compounds, those are crystalline solids. Those covalent networks, those are typically crystalline. The metallic bonding we saw, that was definitely amorphous. Those molecular solids, they can sometimes be crystalline, but they're more typically amorphous. All right, so just a couple of things to keep in mind as we kind of analyze these different solids and different states of matter with thinking about their intermolecular forces.